Welcome back to Chad Bemis's Healthcare Statistics course. Today we're going to talk about expected value, Module 8.2. All right, so let's say that you're playing a game at the carnival. It's a 3-coin toss, okay? Maybe a nickel, maybe a dime, maybe a quarter. All right, it's $1 to play the game. All right, so if all 3 heads or all 3 tails come up, then you win $3. But since you paid $1, you get to keep 2 of them. Okay, you get to keep 2. So keep $2. All right. So should we play? Is this something that is this something that we're expecting to win money over time? Okay. So this is what we're going to talk about today. All right. Now, what this implies is that anything other than all 3 heads or all 3 tails, we lose the $1. All right, so again, random variable we've talked about in the last presentation. It's a variable whose numeric value is determined by the outcome of a random experiment. Tossing a coin, in this case, 3 times, could be rolling a die, could be testing a drug, and so on. All right, it's usually denoted by X, Y, or Z. X is the common one. Today we're going to use we're going to use the letter Y at least once. Okay, the probability distribution, the table or formula that lists the probabilities for each outcome of the random variable. Remember that we usually have X and then we have P of X. So the expected value E is going to turn out to be the mean of the probability distribution, the mu, right? The mean value of that probability distribution. And the way we calculate it is it's the sum of all the X times P of X's. So I would take all of the numbers here and multiply them by their corresponding probabilities and then add those up. Remember, the sigma means sum. Add them up. All right, so as I mentioned, the expected value is actually the mean of the random variable. This strange notation here, once again, this means a summation, and we're multiplying 2 numbers together. If I say P capital X equals little x, what I'm basically saying is the probability that the random variable has a particular value. So little x usually means the little variable could be 0, 1, 2, 3, 4, 5, and so on. All right, so remember that the number of outcomes we talked about in the basic probability section, not only the number of outcomes, but what they are, right? So if all 3 of them come up heads, remember that's a win, right? So the probability of all 3 heads was 1 out of a possible of 8, right? Remember the 8 are, again, HHH, the sample space, HHT, HTH, and so on. Right? There's 8 of them. The probability of getting all 3 tails is also 1/8. The probability of getting exactly 1 head, or let's say anything else, right? So HHT would not be a win because you didn't get all 3 heads. HTH would not be a win. So basically all the other 6 options, we'll call that ALT for alternate, is 6 out of 8, right? So here would be a win, here would be a win, everything else would be a loss, okay? That's basically what we have. This is a W. All right, so again, the sample space includes all of these. These are wins, and the rest are losses. Okay, so the question is, should you play this game? So again, 1/8 for, again, remember X is the number of heads here. So you can imagine what 0 heads means. 0 heads corresponds to all of them being tails, which is TTT, which is a probability of 1/8. All 3 heads is also a probability of 1/8. Exactly 1 head, 3/8, because it's head, tail, 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 head, tail, which is that one. That's HTT. And TTH. So there are 3 cases where we have exactly 1 head show up on the coin. And analogously, there's 3 out of 8 where exactly 2 heads show up. Okay, so that's the probability distribution there. All right, so we could also do this with the sum of 2 dice. In fact, we have done this in the last presentation. Remember, I used diagonals, right? So this was 1 out of 36 for a sum of 2, right? For a sum of 3, it was 2 out of 36, and so on. So this is the entire distribution here that we created in the last slideshow. So you can see that the most likely number, or the most likely sum, is 7, because it could be red 6, black 1, red 5, black 2, red 4, black 3, and so on. So these 6 cases add up to 7. All right, so same example we used before. Would we play this game with someone else? In other words, would we make money? So here's the probability distribution once again for those 3 tosses of a coin. So this represents the row of wins, in other words, amount of money in dollars that you either win or lose in each scenario. So if there's 0 heads, that means it's all 3 tails, which means you win $2. In other words, you pay $1, you get 3 back. If you're paying $1, that's +1. If you get, if you pay $1, that's -1. You get 3 back. That's a net gain of $2. So that's where the 2 comes from. It's a net gain. Net gain. Okay. All right. So the expected value, E, is the sum of all the W times the P of W's. So once again, we could do, let me erase these. We could create a new row below for W times the P of W. So we would multiply these 2 numbers together. Okay, since we're talking about money, we should probably use decimals. So 2 times 1/8 is 2/8, which is 1/4, which is 25 cents, or 0.25. Okay. Here we get -3/8, which is -3 divided by 8 is -0.375. This is also -0.375, and this is going to be positive 25 cents. So we basically add up all 4 of these numbers, right? So the sum is going to be 0.25 minus 0.375 minus 0.375 plus 0.25. Now, of course, I don't have to turn them into decimals and then add them. I can do it all in the calculator in one fell swoop. So I can do -2/8 plus -3/8 plus, this is a positive 2/8. So 2/8 plus -3/8 plus another -3/8 plus 2/8. So I can either add the fractions together or I can add the decimals together, whatever's easier. So the result is -0.25. So let's interpret that, right? That means that we would expect to lose, on average, we would expect to lose 25 cents on each time we play. So on each play. So each time we play the game, we expect to lose 25 cents on average. So if we played it, 100 times, the average loss per time is 25 cents. So if you played it 100 times, 25 times 100 would be, you'd be losing $25 out of the $100 that you bet. So if you started with $100, you'd expect to have about $75 left. So that's what that means. So when the expected value is positive, that means that you expect a win overall. When the expected value is negative, you expect to lose in general. Okay. So again, on average, we expect to lose 25%, 25 cents, per game over a period of time. So maybe not the best idea to play this, since you'll be losing money over time. All right, here's a healthcare example. A group of college students were surveyed to learn how many times they had visited a doctor in the previous year. Learn is actually maybe not the best word. I'll just say surveyed on how many times they had visited a doctor in the previous year. So capital Y is the number of visits, okay? So what we've got here is this probability distribution. So what we can do is create Y times P of Y, and then add those numbers up, because remember that the sum of the Y, PYs, that's the expected value. In other words, that's the average number of visits for each of these patients, or each of these college students. Same thing. All right, so again, here we would multiply the number of visits times the probability of the visit, but 0 times anything is 0. 1 times 0.5 is 0.5. And 2 times 0.35 is 0.70. So I would add these numbers up to determine the expected value. So I would say 0.5 plus 0.7 is 1.2. So the average number of visits for each patient per year is 1.2 visits. So again, we're finding the mean here, but the way we calculate the mean is we use the value, number of visits in this case, multiplied by its probability. So you might wonder, well, where did these probabilities come from? Well, there was probably a sample taken, and 15% of the students, 15% of the students visited their doctor, didn't visit their doctor at all, right, that year. That's what that means. 50% of the students visited their doctor once, right? And 35% visited twice. So that's what we're talking about here, right? That concludes the show.